All right, well, welcome back. It's been a couple, probably maybe a couple weeks even for you guys since the last time I posted a video. I tried to break apart the videos between the first half and the second half here. So hopefully by the time you guys see this, it'll be after the first exam, which really does mark a good kind of break point in the semester there in terms of the major concepts that we have to introduce. And so the first half of the semester, we really talked a lot about the aromatic compounds. And the second half of the semester, where we're going to spend most of our time, is with carbonyls. And so we're going to talk about aldehydes and ketones, which we have talked a little bit about before, at least in the first semester. And what we're going to introduce is some of these other less discussed carbonyl compounds, at least in the first half. So we're going to talk about acyl halides and anhydrides and carboxylic acids and amides and some of these carbonyls that we made you guys understand or at least memorize the name of the functional groups for, but now we're going to come back and actually do some chemistry with them. And so chapters, it's 19, 20, 21, I believe also. Yep, 19, 20, 21. And even a bit of 22 is where we're going to be spending the rest of our time with. So basically 19 through 22 is the next major chunk of stuff that we're going to deal with. Normally I would be breaking these, I would be rearranging the chapters a bit. So, but because of this asynchronous format here, I didn't want to be jumping around if I didn't have you guys in the classroom with me. So I'm just gonna go back to following the book and the way that it's kind of laid out there and hitting the major key points with that. And as always, just please don't hesitate to get in contact with me in whatever means you guys need to, and we can work this stuff out. But so let's start to introduce this idea of aldehydes and ketones, or at least let's knock the rust off of some of the stuff that we have already learned. So remember, with aldehydes and ketones, oops, I need to get my pen going there. So when we are talking about, it's early morning, so pardon my lack of writing skills at the moment. So when we're talking about aldehydes and ketones or carbonyls in general, really what we have to recall is that the generic, let's put some color in this so that it stands out. It's a red and green type of day, so let's do that. So any carbonyl compound is going to have the carbon double bound to an oxygen in there, right? So it doesn't matter, aldehyde, ketone, carboxylic acid, blah, 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 right? Any of that kind of stuff. This is key. It's probably going to take me, I don't know, 6, 7, maybe 8 videos to get through all this carbonyl stuff with you guys. But I could tell you what I'm about to say and then just say, all right, well, we spent 5 minutes and that's really all you need to know, okay? It's true. In fact, the book does a really good job talking about it, and it's going to say the exact same things, really, that I would tell you guys anyway. So when we're dealing with a carbonyl compound, right, we're dealing with a C with a double bond to an oxygen. So let's pause here and really kind of dissect this. I'm going to spend a lot of time on this, or a proportional amount of time on this, just to get this point across, because this is it, okay? Because all the other reactions that we're going to learn are going to say, what's the mechanism? What's the mechanism? And we're going to go back to this exact same concept here, all right? We have a carbon, which is doubly bound to an oxygen. So we have a less electronegative atom, okay? We have a less electronegative atom with the carbon bound to a more electronegative atom with pi bonds present, okay? So we have a less electronegative atom bound to a more electronegative atom with pi bonds present. That's going to be a characteristic of multiple reactions that you guys will see or could see in organic chemistry, okay? We're going to come back to the same principle when we talk about amines, which are related to carbonyls, and we'll discuss that a little bit more, right? We're going to come back to this exact same concept when we talk about amines and cyano groups, where we have a carbon less electronegative bound to a more electronegative atom with pi bonds, okay? there's a lot of information packed away in that very short statement there, right? The first thing is that the carbon is less electronegative, right? And hopefully at this point, in fact, I know at this point, 100% of you guys are like, okay, I understand electronegativity and its implications, right? What we're saying then, right, just to make it extremely explicit, is that that carbon has a partial positive charge, not a full positive charge though, okay? There's a very important distinction with that. The distinction being partial positives, right? Not every partial positive is the same, okay? It's sometimes like, if you've got you wake up and you're feeling good, right? You have a positive attitude in the morning, right? But maybe some days you ran out of coffee and maybe you're not feeling as good that day, right? So you're not as positive. Okay, that's a bad example. But maybe, hopefully you guys understand what I'm saying, right? Not every partial positive is equivalent, right? Not every partial positive is equivalent. And that's going to be important. I'm telling you guys that this is positive. And you guys are like, yep, it's less electronegative, we got it. You've said this 15 times already, move on, right? It doesn't mean that it's super duper duper positive, that every negative, right? It doesn't mean that every negative is going to go after that. Sometimes we're going to have to give a little bit oomph, right? Sometimes we're going to have to give that negative a little oomph. Pardon me, just dropped my pen there, right? We're going to have to give a negative some oomph, some motivation to go after that partial positive. We'll talk about what that means, okay? This is partially positive, that is partially negative. Does that mean that that partial negative is always going to be super duper duper negative, where it's always going to go after positives? No, it does not, right? So in both cases here, we have a carbonyl compound, and we're going to talk about positives and negatives a lot. And we're going to do a lot of reactions with carbonyls, to the point that we might say that, yep, everything negative is going after that carbonyl carbon. That's what I'm trying to avoid, okay? Carbonyls are extremely useful synthetic functional groups. We can do a lot with them. We can bring molecules together. We can change them into a variety of functional groups, okay? We can do a lot with them. They are diverse in their reactions, but that doesn't mean that they just are unstable to the point that they want to react with everything. That's really the point that I'm trying to get across, okay? So let's expand on this for just a second, okay? Or continue to expand on this, I really should say. So if we have something negative, right? So Mr. Generic Nucleophile, okay? If we just have something negative around, it's got to be a pretty strong negative charge for it about to come and do what we want to do, unless there's something else with it, which we'll talk about, okay? So assume we have a strong nucleophile. Then what's going to happen is its point of attack is going to be at that carbonyl carbon, okay? Now, we make a bond, we break a bond, okay? So what's going to happen is we're going to attack that carbonyl carbon. It's going to pop up that pi bond, okay? Let's go with green. I got my carbonyl carbon. There's that. This is still in blue. This is in red. Let's add my lone pairs here to an oxygen, and there is my nucleophile, okay? Under basic or nucleophilic conditions, under negative conditions, we're going to see the attack on the carbonyl carbon, okay? Does this make sense though? I really want you guys to pause and think about this. I just presented you guys something. You're like, yep, it's in the book. This guy checked. Like, why? Why does this make sense, right? So let's think about this for just a second, right? Where are we putting the negative onto, right? We don't know what this nucleophile is. It could be a lot of things, right? Assume it's a grignard, right? Let's assume it's a grignard. And so we have a carbon with a negative charge, okay? If we have a carbon with a negative charge, what do we end up doing? We end up trading that, right, for an oxygen with a negative charge. Now, what do we know about oxygens with negative charges? Well, they're okay, right? They're pretty darn okay at stabilizing that negative, right? So it all depends on where the negative starts and where it ends up. Now, we know that things don't exist just as a negative charge by itself. There's counterions and all that kind of stuff there too, right? So under negative conditions, this is what's going to happen, okay? If we take this exact same idea, and I'm going to just copy and paste this, well, actually, you know what, that's probably not going to help. So I'll just rewrite it real quick. I think you guys know what the next set is going to be anyway, right? If we've dealt with things under negative conditions, then we will come back and we'll say, what if we're under positive conditions, right? What if we have acidic conditions around? Well, if this is a partial positive, right, and this is our partial negative, then you guys see what's going to happen here, hopefully. Right? So under positive conditions, we end up with this. Now I can do that. Make life a little bit easier. Good. What did we end up doing, right? You guys are like, yeah, negative, positive, bring it, right? I ended up putting a positive charge on an oxygen. That's not a good thing, right? Does that make sense? Remember, I'm just basically asking the same thing. Why does this happen, right? Well, we end up putting a negative on an oxygen. That's not too bad. Now I'm saying we have a positive charge on an oxygen. Well, a couple of thoughts again, right? It's a formal charge. It's a formality, right? It's a way of us counting electrons and saying, this is a little bit unusual, right? We know, or we understand at this point, that an oxygen doesn't really have a positive charge, right? We can show that multiple ways, right? The positive charge here is indicating something odd is happening, right? But there's something else that we should be paying attention to, and that's our pi bond right here. Just like in this example here, where our nucleophile comes in, hits that carbon, we make a bond and then we push that pi bond up into a lone pair. Right here, what you guys should be seeing is, oh, I can draw a resonance structure with that. And that's exactly correct. Okay? So let's draw a quick resonance. Oh no, am I going to run out of room? Yes, I am. Let's do this real quick then. And just shift everything over. Perfect. All right. So resonance structure here, right? We can push that pi bond into a lone pair, and we can drop, whoops, I forgot the important thing, pardon me, right? There it is. Lone pair, neutral oxygen, positive charge on the carbon, okay? We could draw our arrow to go back to where we started. Remember, with resonance structures, we always need to be able to go back to where we began. Although hopefully at this point, I expect that everyone should be able to draw these resonance structures here, okay? So what does this end up doing though? This is important. What does it end up doing? What we end up doing is making this carbon feel even more positive. Now this is not the dominant resonance structure at equilibrium, right? This is going to be the more favored resonance structure. Why? Right? So, but remember what's a consequence of resonance structures is that they all exist to whatever percentage or is reasonable for them. Well, not reasonable, what's the word I'm thinking of? They all exist to whatever percentage is equivalent to their stability, if that makes sense, right? It makes sense in my mind, but it is a little bit early still too, so. But anyway, the point being that just because this is the favorite resonance structure, it doesn't mean that this one doesn't or can't exist, right? And so the consequence is that our carbon ends up feeling a little bit more positive. It's got an open set of orbitals in there, right? It's got a less populated orbital in there, right? And so then whatever nucleophile is going to come in next will attack that carbon. In fact, water can come in now and attack that carbon. okay? And you're like, well, okay, that makes sense. We've seen water attack a carbocation before, but do you get the point? The point being, if I just have a ketone without any acid, right? If I just have a generic, right? You know, if we take our good old buddy acetone, okay, the simplest of ketones that we can make, and I add water to it, really, oops, got a little bit too excited there with positive charges, right? If I just mix acetone and water, nothing's going to happen, right? We can make a solution of acetone and water and we sell it as nail polish remover, right? If I add some acid into it, then we start to do a reaction. We start to hydrate our ketone. The point being, right? The point being that the acetone and water, right? Water's not a strong enough nucleophile, right? Water's not a strong enough nucleophile to go after that carbon just by itself. It needs some acid in there to set up the situation where the carbon feels more positive, okay? So this goes back to concepts that we talked about with SN1 and SN2 and E1 and E2 there. The strengths of nucleophiles, how negative something is it a strong base? Is it a strong nucleophile? Is it a weak base? Is it a weak nucleophile? So all those ideas that we did for assessing the relative strength or how negative something is comes back here also, okay? So at this point, hopefully, again, we all understand that water, not a great nucleophile at all. But if we add some kind of catalyst into there, right, something to get the reaction going, something to make a positive charge appear, if you want to think about that, then we can start to add water to our ketone or aldehyde also, okay? Everybody catch along with that, right? If we're under strongly negative conditions, attack at the carbonyl carbon. Positive conditions, we're going to attack at the carbonyl oxygen first, and then we can have our nucleophile that comes in, okay? So these are the main principles of how everything's going to work. Now there's something else that's going on behind the scenes, okay? So let's talk about a little bit more, right? I'm trying to lay a good foundation for you guys, and then we can come back and, you know, do all the reactions that come with it, right? A carbon doubly bound to an oxygen there's a strong, let's say, electronic argument to making carbonyl compounds. Here's what I mean. Carbon-oxygen double bonds release a lot of energy. They are good bonds. There's a drive to make carbon doubly bound to oxygen. And initially you might say, oh, okay, I'll take his word for it. Well, let's think about this a little bit more. Now, keep in mind I'm being a little bit hand-waving here. When you burn something, what happens? Well, under an ideal combustion, right, we take some kind of fuel source and we turn it into carbon dioxide and water, right? So CO2, what do we see in CO2? Well, we see a heavily oxidized form of carbon, right? Where we see a carbon doubly bound to two oxygens in there. So we can kind of intuit our way to thinking that C double bond to O, there's a strong drive to form these. And in fact, right, we're going to see that being used quite a bit. What we're going to see is this mechanism where we open the door and we close the door, as I call it, all right? So what's going to happen is we break that pi bond, right? We break this pi bond and it's going to want to reform and kick something off, okay? So there's a strong drive to reform carbonyl compounds. We have a nucleophilic attack. If one of these was a good leaving group, we would see that double bond reform and kick off a leaving group. So again, we go back to this idea of SN1 and SN2 and E1 and E2 and say, what is a good leaving group? Because if we identify any of the three components, those R groups or that nucleophile as a good leaving group, once we attack, we open the door by kicking up the pi bond, and then we close the door by reforming the pi bond and kicking something out, okay? And so we're going to see this idea come in there again. So to recap here real quick, right, we need to be able to identify strong bases, strong nucleophiles. We need to remember the difference of what happens under acidic and basic conditions. We need to be able to identify good leaving groups. So far, I could have kind of just taken this exact spiel and gone back to substitution and elimination reactions. There's really nothing different. And so I hope you guys are getting the point, okay? The point being is I'm trying to build upon what you guys already know. This might look new, and we're going to spend a lot of time in these chapters and all this kind of stuff, right? But at the end of the day, the same principles that we had to describe the substitution elimination reactions, we're going to be using them again here, okay? There's not going to be anything really different with that. All right, so let's spend the rest of our time here just doing a little bit of recap, because we have already learned some ways that we can make aldehydes and ketones, right? So let's go back and do a little bit of review here. We'll learn how to make some aldehydes and ketones, and then we'll come back and do some new stuff with them, right? Now, let us talk real briefly about some definitions then. Oxidation and reduction. I know I've mentioned this before in one of my previous videos, but if, well, whatever, right here it is again. So when we are dealing with oxidation and reduction in organic chemistry, we can kind of hand wave some of these more complex definitions and just say, are we adding bonds to oxygen or removing bonds to oxygen? Of course, that's not the all-encompassing definition, right? But, you know, it's a fair description, especially for these chapters that we're going to be going through. So, with that in mind, let's make an aldehyde real quick. I'm going to go ahead and draw it like this, right? And I think you guys can see where this is going to go. So if I have a primary, a primary alcohol, I don't know why that didn't come through. If I have a primary alcohol, how do we know it's primary? Well, again, I expect you guys know at this point, right? But if we have a primary alcohol, how can we turn that into an aldehyde? Now, this is actually one of the trickier reactions to do in the sense of there is a drive, just like what we talk about with combustion and making pi bonds and all this kind of stuff, right? There is a drive to turn primary alcohols into carboxylic acids, especially, right? To really oxidize them, right? And so we have to kind of tweak our conditions a little bit to stop at an aldehyde. When we are doing oxidation of alcohols, the primary alcohols are the ones that we really have to pay attention to, okay? Because we can oxidize them all the way into a carboxylic acid if we wanted to. But do you guys remember how to do this, right? This is kind of a review from chapter, I think we learned about this when we were dealing with alkynes, and we talked about this when we were dealing with alkenes also. So the alkenes and the alkynes chapter, and also when we were talking about, what chapter was that in? The alcohol chapter, right? So the alcohols, the alkenes, and the alkynes chapter is where we're going to pull a little bit of information from, right? So this one would have come out of the alcohols chapter. So we have an alcohol, we're going to an aldehyde. We have to give conditions wherein, right? Well, let me give them to you first, and then I can tell you guys the exact thing here. So let's talk just real briefly about the best reaction to do this with. Triethylamine, right, if I am remembering this correctly. Perfect. Okay, so and this is typically done at colder temperature. So sometimes we specify cold or something like that with that, but that's, you know, chemistry on paper. It's not that big a deal for us. So DMSO, oxalyl chloride, and then triethylamine. So this is our good old buddy, the Swern oxidation, so SWERN. Why did I say that this is the preferred way of doing it? Well, a couple of reasons. First is it's the cheapest way, probably. DMSO, pretty darn cheap. Oxalyl chloride, pretty darn cheap. Triethylamine, pretty darn cheap, right? These are common reagents that every organic lab has, right? So it's not some kind of specialized condition, right? It's also pretty darn selective, right? These are going to go after primary alcohols and It will go after secondary alcohols also, right? But these will go after predominantly alcohols and mild oxidation conditions to take those down into the aldehyde. Now, so this would be the way that we would, or very likely, do this in the lab if we had to. Okay, so swern oxidation. Now that's a lot to memorize, right? That's a lot of word salad there. So PCC tends to be the predominant way that I see my students kind of go through this, because it's easier to remember 3 letters rather than all that stuff there with the swern, right? We could even see DMP, the Dis-Martin per iodine, right? I'm sorry, I forgot to say. So this is pyridinium chlorochromate, pyridinium chlorochromate, chromium with oxygens bound to it. If you go back to one of my previous videos, I said this is one of these flags that we should pay attention to dealing with oxidation, right? Dis-Martin per iodine, we don't see any transition metals, but we do have a heavily oxidized iodine inside of a heterocyclic compound there. Very interesting looking structure if you guys haven't looked that up. What else did we learn about this? PCC, PDC, DMP. I think that's kind of all we really need to talk about, right? We don't need too much of a word salad to get through with this. Here's the important part, okay? Well, I'm going to tell you I'll show you the important part. Now, this is one thing that I don't like about teaching chemistry just purely from the books, right? That's always useful to be in the lab to kind of get this idea. So in the book, they talk about PCC and they put it in with the solvent of dichloromethane. And they take DMP and they put it in with the solvent of dichloromethane. Does it have to be dichloromethane? No, of course not, right? And of course it doesn't. But that's the clue with this. The clue for all 3 of these conditions is not necessarily the solvent, but what isn't there. Now, DMSO here is a good solvent also. In fact, you used to be able to buy it many years ago, even before I was born, you used to be able to buy that at the pharmacy. And that'd be an interesting conversation as to why and how and what did it do. But so DMSO is the solvent, typically then dichloromethane and dichloromethane. What you don't see present is any aqueous or water in these reactions, and that's important. Kind of the clue, and if you're, a year and a half from now and you're taking the MCATs and they're talking about oxidations, you're like, oh geez, I forget. Look for water, okay? If you don't have any water around, you're gonna be stopping at the aldehyde. That's kind of the name of the game, okay? Water is the thing that drives this forward to the complete oxidation, all right? And what's useful, and why I'm saying this is a clue, right? So dichloromethane and water aren't miscible. I know you guys are doing video labs. Well, some of you guys are. I know some of you guys have taken this class previously. And so I don't know what they're doing for these labs. I suspect that they've taught you guys at least about extractions and using separatory funnels and all this kind of stuff. And dichloromethane is a very common solvent that we use when we're doing extractions, right? It's a dense solvent, as our halogenated solvents tend to be. And just like chloroform, it's not miscible with water, right? And so it's useful to run these reactions in chloroform because it's a good, dichloromethane, because it's a good solvent and because it tends to be a dry solvent. We don't have to worry about water being around in there. And that's going to help complete our reaction and stop it at the aldehyde there, okay? Got it, cool, right? Do I need to know these mechanisms and all this kind of stuff? No. I know they show the swern oxidation mechanism in there, but not something that I'm going to ever ask you guys to come back at with this, right? Okay, what else do we know? Well, this is a problem that we did in one of our problem sessions here, or similar to it, right? If we ozonate this DMS, right, then we will end up with 2 equivalents of our aldehyde there, right? So an alkene, ozone and dimethyl sulfide, as opposed to dimethyl sulfoxide, right? So DMS, right, we'll take this into an aldehyde. What's useful about this and what isn't useful? What's useful is this is a good way of cutting carbon-carbon bonds and leaving carbonyls behind. And with carbonyls, we can do a lot, right? We can do a lot of chemistry with carbonyls. What isn't useful about this is that it's not very selective. Ozone is a good oxidizing agent. In fact, that's how they purify water, right? I think it's Aquafina. I don't know. Maybe one of you guys can look it up for me also. But one of these common bottled waters, they say it's purified by ozonolysis, which they just make ozone, which is not too hard to do, and they just bubble it through here, and it kills pretty much any biological stuff that's in there, right? So it's purification from biological things, not from metals and other stuff that might be dissolved in there, right? But at relatively mild conditions to cleave an alkene into an aldehyde, right? That's all good. Let's talk about maybe the most useful or most important one for us, right? And that is if we take a terminal alkyne, I have to be careful here. I almost didn't put enough carbons in there. Be careful with those alkynes, right? Always count twice, right? So there's 2 carbons there, 2 carbons there, right? So how can we take an alkyne into an aldehyde? So now we have to really kind of stop and think and remember here. So an aldehyde is terminal. They always have to be terminal. They're always going to be at the end of the chains, right? And so we have to add an alcohol to the less substituted side, and then it's going to tautomerize into the aldehyde itself. Okay, so we only really know one reaction of how we can add an alcohol to the less substituted side, and that is our hydroboration oxidation. I'll come back here in just a second and kind of clarify some things. So we have our hydroboration, so now we need our oxidation, so we got some peroxide, and we got some strong base in there, typically sodium hydroxide. Okay, right? So ignore this for just a second, right? Hydroboration, let me zoom in on that. Right? So hydroboration and then oxidation, okay? One of the most important reactions. Why? Because it's anti-Markovnikov addition of an alcohol. If we do anti-Markovnikov addition of an alcohol to an alkyne, it is going to tautomerize into the aldehyde, okay? Now, technically I have a mistake, okay? We really wouldn't want to use BH3 if we're dealing with an alkyne, just because the way that the borane will react, it'll react multiple times and kind of create a mess. And so what you might see is something like this, SIA2BH, okay? And that SIA just is some kind of alkyl chain. It's a bulky alkyl chain. It's a sec-butyl chain is what it is, right? The point being, we have a hydro and we have a boron, right? So hydroboration and then the oxidation. The rest is the same here. It's just when we're dealing with alkynes, we tend to have these bulky groups on there which kind of shut down some of these side products that might happen with it. Not that big a deal, right? What I want you guys to recognize or be able to understand is hydroboration and how it works, right? This other stuff is kind of, it's icing on there, right? It's the stuff that, well, whatever. You guys get the point, okay? So in the book, you might see these two, or you might just see an R group there. It doesn't really matter. Look for the hydro, look for the boron, then we're doing hydroboration, okay? But this is a fantastic way of making a terminal aldehyde with that, okay? So, all right, let's see what I want to do. Let's talk about one last one then, okay? And this will be a kind of a good thought exercise. I know this video is kind of going on a little bit long here, so I don't want it to end up as a 15-minute rant, but right. Let's shift real quickly then into talking about ketones. Right? How could we do that? Right? How could we take our good old buddy Mr. Benzene and how could we turn it into acetophenone? Right? How could we turn it into some kind of carbonyl containing compound there? right? And that is our Friedel-Crafts acylation, right? So this is stuff that was just on the last exam, although I'm actually recording this before the exam, so I am looking into the future and predicting I will put something on the exam that has this on there, right? It's a good prediction. All right. Oops, I'm being dumb. There it is. I don't need that. Okay. So we have some kind of acyl halide with our metal catalyst in there, and that's going to be adding to an aromatic ring, and now we end up making a carbonyl compound, right? So there it is. Okay? But you'll notice that now we've kind of switched into ketones here, right? So what's the difference? The difference is we don't have a hydrogen next to that oxygen there. Now, let's quickly go through how we can make a carbonyl. Well, we're really going to change things up. You guys ready? So previously, right, if we just go right up here, right, we had a primary alcohol and we said, how could we take that into an aldehyde? Technically, we could take all those, okay? We could take all those there with a secondary alcohol and that would work just fine. So PCC, PDC, DMP, the Swern oxidation, those would all work with these, with a secondary alcohol also, okay? But secondary alcohols, we don't have to worry about over-oxidation, and so we can put chromic acid into these. H2CrO4, okay? H2CrO4. Now, here's where the book is a little bit different, right? So when they talk about chromic acid, they typically put some kind of chromium salt, so Na2Cr2O7, right? And then they put this in with sulfuric acid and water, okay? These are, in essence, equal, okay? When you dissolve sodium dichromate into sulfuric acid and water, we end up making chromic acid in solution there. Why do I almost like this form better? Because it explicitly shows the water, and if we tried to do this with a primary alcohol, it would take it all the way into a carboxylic acid, okay? Right, but with a secondary alcohol, not gonna be a big deal. We take this into a ketone, okay? So all the points with the aldehyde work here also, except we can add in our chromium salts to complete this oxidation, okay? Good stuff. We could go back with our O's analysis, right? And if we have some kind of tetra substituted alkene, right? We do the snip, slide, and slap, right? We just snip that in half. We slide our alkene apart, and we slap some oxygens in its place, right? And we will make two of those again. Nothing really different here. The only difference being the substitution of the alkenes as compared to the other substitution for the aldehydes there, right? So O's analysis works here also. The one difference that we'll spend maybe a little bit of time on here is if we have some kind of non-terminal alkyne, so an internal alkyne there, how could we turn this into a ketone? Now, technically, you could do hydroboration with this also, right? So again, we could just take that the same idea there from the aldehyde, do hydroboration. Hydroboration oxidation doesn't just work on terminal alkynes, right? I think you guys knew that. So we could do the same thing here, but because we don't really have to worry about selectivity too much here with the generic example, right? We can add in our other oxidation form, right? Which is where we can add some kind of mercury salt, okay? And if we put this in the presence of some acid, typically, well, let's bring this down here. Typically some dilute sulfuric acid, okay? So this is our oxymercuration. This is our oxymercuration conditions. We learned about these when we were talking about aldehydes and alkenes and all that. Excuse me, when we were dealing with alkenes and alcohols is what I meant to say, okay? So this is, anytime you see some kind of mercury salt, mercury sulfate, mercury chloride, typically whatever mercury 2 salt we have Under acidic conditions, we will do our oxymercuration. These are our good reactions because they don't form a carbocation, so we're not going to see any migration of the positive charge, okay? That's all stuff that we've dealt with in the first semester there, so I'm not going to go over it here, although please, if you're confused with it, just reach out to me, all right? So, in addition to the hydroboration, now we can add oxymercuration if we're trying to make a ketone there also, okay? All right, so real quick in review here, I'll zoom out here, so let me see if I can catch everything on the screen at once. There's a lot of similarities when we're dealing with what we've learned with making carbonyls, making ketones and aldehydes, I should say. We can use the same reactions for aldehydes to make ketones, but we can't use all the same reactions for ketones to make aldehydes. That's the whole point with it. And it's your job to understand when and where and how to use those. That's what it might be, okay? All right, so that's enough yammering about this introduction for now. I will see you guys in the next video then.